Hey everyone. We have Aaron from Blockstack here. He'll be doing a talk on anchoring proof of transfer. Once he starts talking, can you guys confirm in the chat that you can hear him?
Hello, everyone. I'm Aaron Blankstein, one of the core engineers working on the Stacks blockchain, and I'm going to be talking to you today about one of the sort of core mechanisms behind how proof of transfer works, and I'll also talk a little bit, maybe give a high overview of how proof of transfer works. I'm going to pause for a second while I check that you can actually hear me. Um, yeah, okay, cool. It seems like people can actually hear me. Great, wonderful. Okay, let's get this party started then. Okay, so um, the stacking consensus algorithm and proof of transfer, which is sort of the mechanism behind the stacking consensus algorithm, is a process that, if adopted, will be used in the Stacks 2.0 blockchain. Proof of transfer is a modification of proof of burn mining, where instead of destroying the committed Bitcoin, miners transfer that Bitcoin to Stacks holders who are themselves participating in the stacking protocol. Now, while during this talk, I will give you a lot of information about how these things work. For more details, you should really consult SIP001 or the Blockstack white paper, both of which go into a lot of detail on proof of burn mining and sort of the other components of the Stacks blockchain and Stacks network. And then also SIP007, which goes into a lot more detail on proof of transfer, stacking, and delegation protocols. So to get started, I'm going to give you a very high-level version of how proof of burn operates, and then give you an example of leader election under proof of burn. So in proof of burn, to get started, a miner who's interested in producing, say, the next Stacks block in the Stacks blockchain will begin by committing some Bitcoin to a burn address, thereby burning that Bitcoin to start the process of announcing their block. Once all of the miners for a given block have performed their Bitcoin commitments, the Stacks node network goes through a process of leader election where every node in the network is sort of running the same algorithm, which takes as input all of these miner commitments and produces an output which tells them which of these miner commitments is sort of the winner for that particular block. Once this winner has been selected, that winning miner reveals the block to the network, broadcasts it out. Nodes within the network validate that the block is correct. It corresponds to the assertions made in that miner's commitment, and they append it to the Stacks blockchain. So an example of how this might work, we'll take a look at a Stacks blockchain that has 3 blocks in it right now, and then 3 miners, miner A, B, and C, who are trying to build the next block in the Stacks chain. So each of these miners, in order to participate as a miner, burns some amount of Bitcoin, and they announce which chain tip they're going to be building off of. So miner A and B both burn 1 Bitcoin, and miner C burns 2 Bitcoin. Once these commitments are announced to the network, network participants look at all of these commitments, and they assign a score to each miner based on the amount of Bitcoin that they've committed relative to the other miners. So in this simple example, miners A and B both burned the same amount, so they would have the same score, and miner C burned twice as much, so their score would be twice as high. So the scores here would be something like 0.25, 0.25, and 0.5. Now, based on these scores, the consensus algorithm then assigns a range for each miner, which is going to be used to do a weighted random selection amongst these miners to pick who the winner is. So we have a random process that we call sortition that produces a value between 0 and 1. So in this instance, we produce a value of 0.45. 0.45 falls between the range specified for miner A and miner B. So miner B wins, and then miner B's block is appended to the blockchain. With this system, you're able to produce the Stacks blockchain, run it on top of the Bitcoin blockchain, and have miners participate entirely through burning Bitcoin. Okay, so that's great. Now, proof of transfer is a sort of generalization of this algorithm. In proof of transfer, rather than forcing miners to burn all of this Bitcoin, what the network specifies is that each miner should send that Bitcoin to Stacks holders who are participating in the stacking process. So if we return to this sort of high-level overview of how the network makes progress, here it looks pretty similar, but there's an additional step. So in this step, current holders of Stacks broadcast some Stein statements, complete some requirements like locking up their Stacks in order to be included in the reward set. Once Stacks holders have gone through this process, have gotten included in the reward set, miners at this point who are interested in building the next block on the Stacks blockchain will commit Bitcoin to addresses chosen out of the reward set. Once they've issued those commitments, the process sort of flows along like it did before in proof of burn, where you go through a leader election algorithm to choose the winner and the person that's going to assemble the next Stacks block. Okay, so that seems like a fairly easy modification of proof of burn, but there's one sort of really tricky thing happening here, and that's getting nodes to agree on what this reward set is in the first place. This might not seem like that hard of a problem. So I'm going to go into a little bit more detail about like what can go wrong when it comes to forcing a whole network to come to agreement on this reward set. So reward set agreement is hard. Why is it hard? It's hard because the reward set is really only valid in the context of specific Stacks blocks. Now remember, this reward set is composed of people who have participated as stackers. People who have participated as stackers are people that hold Stacks and have met some set of requirements, and all of these requirements are sort of validated on the Stacks blockchain. However, this leader election and mining process, this all is occurring on the Bitcoin chain. So Stacks nodes that are trying to validate this leader election and all of the mining that's occurring, they need to be able to safely handle any of the problems related to interactions between the Stacks chain and the Bitcoin chain. So in proof of burn, the only things you're really worried about are Bitcoin forks, because those would sort of impact who won different sortitions or different leader elections. But now that we've introduced proof of transfer and this concept of reward sets, forks in the Stacks network can now suddenly have impacts on whether or not a reward set is valid, and then whether or not particular miner commitments are valid. So the goal in designing a proof of transfer algorithm is that we want to be able to prevent sort of complete failure of the chain when you have these sorts of problems. You want to limit the likelihood of these problems ever occurring in the first place. And you also want to reduce the feasibility of like intentional or malicious attacks that would exploit those problems. All right, so let's look at, I guess, one of these problems in a little bit more detail. So here, let's imagine that we have a Stacks blockchain and sort of two Stacks holders in this blockchain, Alice and Bob. Within the Stacks blockchain, there's two forks, fork A and fork B. In fork A, Alice has received from Bob enough funds to participate as a holder in the next reward set, and Alice broadcasts a signed message and is able to participate. Great. Now in Stacks fork B, what happens instead is that Bob spends those funds that would have been sent to Alice. And in this fork, Alice does not have enough funds to participate in the reward set. This is a problem. The reason this is a problem is that now if we have two different miners mining these two different forks, they might have a disagreement about where commitments should be sent to. So like, let's say miner A is mining off of fork A, they commit funds to Alice. Miner B, mining off of fork B, does not commit funds to Alice because miner B doesn't believe Alice is in the reward set. So now miners A and B disagree about how to interpret the leader election results because each of them think the other miner's commitment is invalid. And this problem is true for other nodes in the network as well because they don't know how to resolve the situation. Okay, so this is a problem. So what's the solution? The solution is a concept that we call proof of transfer anchor blocks. The intuition behind proof of transfer anchor blocks is that for each reward cycle, we want to get every node in the network to agree on a single block, the proof of transfer anchor block. And for this block has the property that if you want to determine the reward set for a particular reward cycle, nodes only have to consult the chain state at the time of that anchor block. And what this does is it puts a fixed point in the network that everyone can agree on and say, if you've processed this block, then you know how to perform proof of transfer commitments and you know how to validate them. If you haven't processed this block, then you only validate commitments that are doing burns. So you have a way to fall back to doing proof of burn. Okay, so given that we want to choose an anchor block, what are the requirements that we might want for this anchor block? So we want this anchor block to be very unlikely to be included in a losing fork, right? We don't want this anchor block to be chosen and then most miners in the network actually not following that block, because in that case, very few of the commitments in the network would actually be proof of transfer commitments. It would mostly be burns. Further, we want it to be very difficult for this block itself to have been hidden from the network for a very long period of time, because then there would be some period of time during which the network didn't know how to process proof of transfer commitments and could only process burns. And then it would have to reorg and sort of go back and reprocess things whenever it discovered the anchor block. So to translate these requirements into sort of more technical terms, what we would say is that we want a block that has very high depth, i.e. it's an old block. So most people in the network will have had a chance to see it. And second, that this block has significant miner support so that during the block's lifetime, however long it was included in the blockchain, a majority of subsequent blocks confirmed the anchor block. Okay, so given these requirements, how do we actually select this anchor block? And in the stacking consensus algorithm, we basically break this problem up into sort of a two-phase process. In the first phase that we call the prepare phase, that's when we actually do all the work of selecting the PoX anchor. And then once the prepare phase is finished, we can begin the reward phase. And in the reward phase, that's when miners are actually able to commit their new block funds to the chain using the reward set derived from that anchor block. And an important note here is that these cycles can overlap such that, like, if you're processing a ton of reward cycles, like one reward cycle could still be in its reward phase while the next reward cycle is beginning its prepare. Okay, so let's zoom in on the actual process that Stacks nodes go through during the prepare phase. So the prepare phase itself is a window of Bitcoin blocks before the reward phase begins. Could be something like 240 Bitcoin blocks. And during this phase, we're actually sort of selecting the PoX anchor. So here in this diagram, we have two Stacks forks, a portion of which are occurring during a prepare phase. And the x-axis here indicates the time on the Bitcoin chain when these Stacks blocks sort of won their particular leader election. Okay. So the process that we're going through during the prepare phase is sort of like a vote counting process. So we go through each block in the prepare phase and count which anchor block that particular block is voting for. And the block that each block is voting for is its latest ancestor that occurred before the prepare phase started. So here we have the requirement that the anchor block is sufficiently old. And then we're doing this vote counting to make sure that the anchor block is sort of sufficiently confirmed by enough miners. Okay. So let's count the actual votes here. So for the first block in the prepare phase, its latest ancestor before the prepare phase was just its direct ancestor. The second block in the prepare phase votes for the same ancestor. But the third block, because it's on a different fork, has a different latest ancestor before the prepare phase. And so it's voting for a different anchor block. And then the last two blocks in the prepare phase extend the top fork and are, of course, voting for that same anchor block. Now that the prepare phase has ended, we reach prepare end, we tally up these votes and figure out who the anchor block should be. So the anchor block is the block voted for by a large majority, for example, 80% of prepare phase blocks. If no block receives a sufficient number of votes, like there's high contestation in the network, then no anchor block may be selected. But here we've chosen this block as the anchor block, and we're ready to begin the reward phase. Okay. So in the reward phase, miners compete with each other to assemble the next block by broadcasting block commitments, sending Bitcoin commitments to valid addresses. If a miner is building off a descendant of the anchor block, then the only valid addresses that they can send to must be selected from the reward set. So if you're building off the anchor block, as a miner, you commit to the reward set. If you're not building off the anchor block, or you're not descended from the anchor block, I should say, then you must burn your commitment. So you fall back to proof burn. And then finally, if an anchor block was chosen, but your node hasn't processed that anchor block's data yet, then your node must treat the reward phase as if an anchor block wasn't chosen. So in this way, if there's a problem in the network, your node falls back to a proof of burn system. So returning to the mining diagram that we had before, when the prepare phase here ends and the reward phase starts, miners begin competition to extend the blockchain. So if miners are continuing to mine off of these two forks, miners that are mining on the top fork, because it's a descendant of the anchor block, they're actually committing their Bitcoin to addresses chosen out of the reward set. If a miner is building off of the bottom fork, because this fork is not descended from the anchor block, these miners actually burn their committed BTC. So those miners are, in some sense, falling back to a proof of burn system. Okay, so to summarize what's going on here, proof of transfer is a mining protocol that supports a system like proof of burn, right? It supports a forkable blockchain built on top of an underlying burn chain, with the key difference being that proof of transfer allows miners to transfer their funds to participants rather than burning those same funds. And in order to support proof of transfer, we use a process called anchor block selection, which allows proof of transfer to operate in the face of terrible events like network partitions, forks, or sort of other malicious activities on the network. And the key insight of anchor block selection is that it works by optimizing for the normal case in the network. So in the normal case, an anchor block is a block visible to all forks in the network and almost all forks build off of it. So in the normal case, you would expect most miners to be participating through proof of transfer. But in abnormal cases where there's a lot of contesting between different miners, or there's network problems that prevent blocks from being broadcasted in a timely manner, the network itself continues to operate by falling back to proof of burn. Cool. And with that, I'm happy to take any questions that people might have. And if there's not enough time, I guess, in the talk slot to take those questions, I'll be in Discord for a little while. So thank you all for listening to my talk. Okay, I have to figure out how to find the Ask Question tab. Oh, I see. Okay, so what if you want to be a Stacks miner, but because of your location, you cannot purchase the STX tokens from Randall? Cool, that's a good question. But let's see. So in order to be a Stacks miner, you actually do not need to be yourself a Stacks holder. So in order to mine Stacks, all you need is Bitcoin. So in a proof of burn mining situation, you would have that Bitcoin and you would burn it. In a proof of transfer situation, you use the reward set to determine where to send your Bitcoin in order to participate as a miner. So yeah, to participate as a miner, you don't need to be holding Stacks, you just need Bitcoin. Question. Okay, we also have a question from Pascal. If a miner does not mine off the PoX anchor, is there a possibility that some stackers won't get transferred a reward? That's correct. So the reward set for a given reward cycle is sort of traversed in order in each sortition. And so if many miners are trying to fork the blockchain and fork away from the proof of transfer anchor block, they might burn during a block in which a stacks holder or stacking participant would have been receiving a reward. So if all of the miners decide to burn instead of build off the anchor block, then yes, some people would be losing out on rewards. Cool. And then we have a question from Ryan. Any implications around high fees on BTC and how this might interplay with PoX and Blockstack? So yes, the answer is high fees on Bitcoin will impact miner interest in participating as a Stacks miner because they have to go through this process of broadcasting their commitments on the Bitcoin blockchain. So if Bitcoin fees rise significantly, you're going to maybe spend more and more of a fraction of your mining commitment paying fees for a Bitcoin miner. Ultimately, there will be a trade-off here because while you as a miner are sort of like facing this fee, other miners are as well. And so the sort of relative impact to the entire mining pool will kind of be the same. And so if you get over that sort of like fixed cost of paying the Bitcoin fees, the fees of the participating as a Stacks miner at that point sort of remain the same, but it does affect the dynamics. So yeah, good question. Okay, and then we have another question. How much BTC would someone reasonably need to be a Stacks miner? That's hard to say. That's ultimately going to be governed by interest in stacks, interest in stack mining, all sorts of stuff like that. And that's really something that you can't say until basically mainnet. Okay, and then Pascal is a follow-up. So if a miner does not mine off the PoX anchor, that miner is guaranteed to not get the STX reward. So that's not quite the case. That miner will get a STX reward if the block that they mined eventually becomes part of the dominant fork. Of course, that's really hard to do if an anchor block was chosen, because if an anchor block was chosen, what it means is that that anchor block is really old, so it's 240 blocks ago, and it's received a super majority of confirmations. So it's like a very deep, very well confirmed block that will be very difficult to fork away from. So if a Stacks miner is building a fork that's not descended from that block, it will be very difficult for that miner to eventually become, or it will be very difficult for that block to become the dominant block. So it's unlikely that that miner is going to see the stacks reward for that block. Cool. And then a question from Tarun. Any additional tools and works that makes stacks mining deployment even easier? I think that there is a lot of work going on in tooling around the Stacks blockchain, making building it easier, making running it easier. We're sort of actively working on interfaces around mining, trying to expose an API for people to use to sort of write their own sort of intelligent miners and stuff like that. So yeah, there's a lot of work there, but also happy to sort of have community involvement in beefing up that process, making it even easier to participate. Cool. Well, those were really great questions, everyone. And like I said before, if you have any other questions, I'll be around in Discord for a little bit. I'm also sort of just generally around. You can email me at Aaron@Blockstack, or just file issues on GitHub and stuff like that. So yeah, thanks everyone.
Yeah, this is great. Thanks so much. We're going to transition to next talk now.